Now in this lecture, we shall be discussing in much more detail about the what we can say bending moment capacity. Now this lecture might be a little bit difficult if you are doing this calculation for the first time. But let me assure you that by the end of this or by the end of next lecture, you shall be fully comfortable what exactly is the meaning of laterally unsupported beam and how we can calculate that. And we shall be discussing that with the help of the practical example also, that the theoretical example calculation and the by doing that in the ETAP software also. So as I said that if we first of all talking about the bending moment capacity, we had already discussed that that is nothing but m equal to sigma into z, or like it is also known as Fy into Zx. So Fy is the yield stress and Z is basically the second moment of area, or we can say effective sectional modulus, sorry. So that again needs to be multiplied with the phi, that is strength reduction factor, that is 0.9 for that. Now after that, if we are talking about the what we can say the bending moment capacity, I should talk to you about the two different terms first of all. The first term is basically the m naught. Now m naught is the what we can say as the reference buckling moment. Reference buckling moment. Now you have already studied the design of the columns, and why we are talking about the buckling behavior when we're talking about the beam is that basically what happens is that steel, instead of yielding on the what we can say as a tension phase, it basically buckles. So that is why we are talking about what we can say as the reference buckling moment. So that value is nothing but that is equal to what we can say pi square E into I y divided by L square, L effective square. So this is nothing but the same Euler equation that you must have studied in your university also. So pi square, the value of pi is 3.14, E is the modulus of elasticity, and we very well know that I is basically the what we can say as the moment of inertia, and that is divided by the LE, that is the effective length. And after that, that is basically again multiplied with another square root term. That square root term is nothing but g into j plus again pi square eiw divided with the le square. So here we are talking about what we can say as the simple basic equation of the buckling, but in here instead of iy, that is the moment of inertia for the y-axis, we are talking about the iw, and iw is nothing but the warping constant. Iw is warping constant. So that is again divided with le square. So this is the basic equation to calculate what we can say as the reference buckling moment. Second term that you do need to understand is alpha s. Now basically if you're talking about the what we can say as the alpha s, that is nothing but 0.6, and that is again that is square root of msx divided by m naught square plus 3, and this whole we can say equation, yeah, so that is needs to be subtracted from msx divided by m naught. So in here we're talking about the alpha s also, we're not talking about the m naught also. So let me just first of all write all these we can say equations. We have understood about the m naught, we talking understood about the we can say alpha s. After that we shall be discussing about the third term, that is what we can say as the alpha m. So alpha m is equal to what we can say as 1.7 m to the we can say we can write it as a star divided with the square root of m2 square plus m3 square plus m4 square, and that needs to be less than 2.5. So These three are the factor which we can say are important if you want to understand the design of laterally unsupported beam as per the AS 4100. Now in these we can say these two terms, that is alpha S and alpha M. These two are interdependent, or we can say dependent on each other. Basically, alpha M into alpha S, that needs to be, we can say, less than 1.0. So in majority of the cases, like alpha M is a high value and alpha is a value that is in like in quite in decimal itself. So alpha is basically determines that what exactly is the slenderness behavior, or whether the section itself is slender or not. So for slender, alpha S is very less, but if the section is stocky or bulky or big in size, in those cases alpha S is high. Alpha M is the one which is dependent on what we can say as the bending moment diagrams. So alpha M is different if the beam is simply supported. Alpha M is different if the beam is cantilever. Alpha M is different if beam has some, we can say, different restraint conditions. So that depends on the alpha M here. So here you can see that basically we're talking about the bending moment itself. So all of these, three parameter alpha M, alpha S and M naught. These three are the factor which also determines the bending moment capacity of laterally unsupported structural steel beams. So as of now, you can just write these formulae. What we shall do is that we shall be calculating this in real very shortly in this particular example. So let me just show the example. So before, we do keep on repeating the theoretical calculation, we shall start doing the practical example itself. And then we shall go back to the theoretical, we can say, concepts that we were discussing, so that the things become, or the concepts become clear to you. So first of all, if we want to talk about the span of this beam, let us say the span of the beam is, the title is basically simply supported beam, unsupported full span. So let us suppose the span is approximately 8 meters here. And the loading, so the let us suppose the permanent load is approximately 15 kilonewton per meter. The live load, or we can say imposed load, that is approximately 10 kilonewton per meter. And we can say that basically it is nothing but the simply supported beam, which for which we can calculate the bending moment by WL square by 8. So by putting that value, the bending moment is coming approximately 273.6 kilonewton meter, and the maximum shear force that is coming is approximately 136.8. So the loading is clear, and after that we can say the load combination, that is 1.2 times permanent action plus 1.5 times the imposed action. So the bending moment comes out to be M maximum comes out to be 273.6. That can be simply supported with the help of we can say calculated with the help of WL square by 8. We can calculate that also if you want to cross check the results. So our total UDL, that is approximately 25, and that needs to be multiplied with L square, that is 8 into 8 divided with 8. So the value comes out to be 200, but you do need to understand that the beam has a self weight also. So to consider self weight, what we need to do is that we do know that this weight is approximately 15 kilonewton per meter, and this is 10 kilonewton per meter. And in addition to that, the UB that we are considering, that is approximately the size is UB 610 into 101. So considering that particular size, we can say that the unit weight is approximately 101 kg per running meter. So 101 kg into 9.8, that is in Newton, divided by 1000. So that is approximately what we can say as 1 kilonewton per meter. So what we can do, we can simply 25 plus 1, that is approximately 26, and that is our UDL into, we can say, L square, and our span is approximately 8 meters. So you do need to understand that to calculate the bending moment, we do have to multiply. First of all, the permanent action, the factor is 1.2. So 15 into 1.2, that is approximately 18. And the second one is approximately 1.5, the imposed factor. So 10 into 1.5 is 15. So 18 plus 15, that gives us value of 33 kilonewton per running meter. And the UB that we are having, that is UB 610 into 101. So that is having unit weight of approximately 1 kilonewton per running meter. So that also needs to be added to this. So 34 we can say needs to be multiplied with the span WL square divided by 8. So the answer comes out to be approximately 272 kilonewton meter. And the one that we are considering is approximately 273.6. So that we can adjust. Similarly, for this also, we do know that our the shear force here, that is approximately we can say WL by 2 or divided by 2. So in our case, it was approximately we can say W was 36 into 8 divided by 4. Sorry, divided by 2. So similarly, we can calculate the shear force also by using the formula of W into L by 2. So W we have already calculated a few minutes back, and according to that, we can simply find out the shear force value also. So this is clear. Maximum shear value is also clear, and the deflection that can also be calculated with the help of simple formula, that is 5 WL4 by 384 EI. So all of these, I'm not repeating that because that is a basic calculation which everyone know. So this is 9.1 mm, and maximum reaction we know is 136.8. And these are the like basic calculation, the unfactored permanent load, unfactored imposed load. So that is okay. So after that, the beam that we're considering, as we know, 610101 of 300 grade. And the thickness of material, that is approximately what we can say maximum of TF by TW. So it is 14.8 mm. So considering yield stress of 300 Newton per mm square and tensile strength of 440 Newton per mm square, as the thickness of the that is between 11 and 17. If this thickness would have been less than 11, we might not have been able to use the complete Fy. We may have to reduce it to 290, the Fy value. So that is the importance of the thickness. After that, we do know that capacity factor phi is 0.9. So all of these are like the basic calculations. So the first step that we do need to do is that we do need to find out whether the section that we are having is compact or the section that we are having is non-compact or the section that we are having is slender section. So what I shall do is that I shall again, take a few minutes of your time and try to, explain the meaning of the compact section, non-compact section, and slender section. See, before that, I just want to, explain about what different countries are doing. So in some of the countries, they do have 4 different categories: plastic also, compact also, non-compact also, and slender also. But as per the Australian standard, we do have only compact, non-compact, and slender. So we do have 3 types of, we can say, categories for the sections. So in compact section, basically, we can say that there is no possibility of local flange or web buckling. So local flange, or we can say web buckling, that won't happen. So that we can simply cross. So we can say that the whole section, we can say, shall achieve the full yield stress depending on the restraining or supporting conditions. So under the non-compact section, we can say that it is possible that some local buckling, we can say, may take place before the attainment, or we can say before achieving full plasticity. So the section might not be, let us say if this is our, we can say, stress strain diagram. So we do know that for Striegel, the diagram is something like this. So this is our full elastic range. If you are a structural engineer, let us say in year 1980s or 1970s in Australia, you might have been, restricting your domain only in this particular area. But as the research, increases, we can say that we can utilize the plastic moment capacity also. So considering what we can say is the plastic moment capacity, we can say that we do have increased strength And on the basis of that, we can, fully utilize the structural steel section, considering that beyond elastic range, there is a plastic range also. After plastic range, the steel section may deform, or we can say elongate, and there may be, we can say, a hinge formation in the, we can say, a non-linear and unsafe hinge formation may happen. So the point that I'm trying to convey is that in compact we can achieve full plasticity. In non-compact we cannot achieve full plasticity. Before that only some local buckling may happen. And under the slender section and slender beam, both of them are different things. First of all, if in the analysis you are having a slender section for beam, then you are doing the analysis wrong, or you are doing the design wrong. You do need to change the section. So it is always recommended that the bending members may be compact or non-compact. The bending members are never recommended to be slender. Slender members are usually used for tension members only. So under the members which are having tension itself, we do use the slender section, but for bending, it is never recommended. In fact, some country codes do not even allow the slender section to be used for the bending, because they perform very poorly at a time of earthquake or at a time of the extreme cyclones. But in Australia, slender section may be used, but obviously at the risk of what we can say, any kind of failure also. So as a structural engineer, I never use the slender section. It is always recommended to use the compact or non-compact section. Although the code do guides us that how we can design the slender section for bending also. But as an engineer, I never recommend anyone to design the slender members as the, what we can say, structural steel members. So this was the basic introduction to compact, non-compact, and slender. Now, how we can determine the compactness, non-compactness, or slenderness of an I section? We can determine that with the help of the basic formulas. This is basically TW. This is TF, thickness of flange. This is BF, width of flange, and this is the depth of the web. So the AS4100 do have various formula which help us in calculation and assessment that whether the section that we are having is compact, non-compact, or slender. So that we shall be doing this here. So in here we do know that for flange slenderness, the lambda EF value. So lambda EF value is BF minus TW, that is the width of flange minus thickness of web, divided by 2 into thickness of web, multiplied with square root of FY by 250. So these are the different parameters which are already given: the thickness of flange, the thickness of web, the width of flange, the depth of web. So on the basis of that, we can calculate the different values of our flange slenderness, and the value comes out to be 8. Now the flange yield slenderness limit as per table 5.2 of AS4100. So we can open that also. So this is the table 5.2, and in here you can see that basically if we are talking about the table 5.2, the plate element type is flat. That is our, if you're talking about the flange here. So this is the flat plate, and on the top of that it is only supported on one side. So longitudinal supported, that is one only. And our the section, that is hot roll section. So there are different kinds of section, that is HR. HR is the one that we are discussing it from the minute 1 of this particular video lecture series, that are like UB, UC, or we can say uniform angles. So these are the sections that are hot roll section. Stress relieved SR sections. So these are the section in which with the these are welded section itself. And stress relieved is the process with which we do ensure that there are no as such very high value of the residual stresses at a time of fabrication of the structural steel beams. So these are LWCF, lightweight, or we can say cold form sections. HW is heavily welded section. So heavily welded are the one like which we do use for, we can say, bridges where the bending moment is extremely high. So in here you can see that yield limit, if you're talking about the hot rolled section, that is 16 in value. So we can check our value here. So in here you can see that that is basically 16. So if this value that would have been 18, so our section would not have been compact in that case. Our section would have been non-compact in that case. But it is a good thing that it is what we can say a compact section. So that is like okay for the flange. If you're talking about the web slenderness, so web is the section we can say that is supported on both the sides. So on the basis of d by tw into fy by 250 square root. So this is the term that shall be multiplied irrespective of whether we're talking about the flange or web. But this is the ratio, that is the depth divided by thickness of web. So this number comes out to be 59.2. And the web yield slenderness limit, that is approximately 115. So that also we can check in what we can say table 5.2. So this is the flat, and as I said that the I section web that is supported on both the sides. So that gives us this particular value, and yield limit that is approximately 115 for any kind of section, whether it is heavily welded, hot rolled, stress relieved, lightweight, cold form, irrespective of that, that is the maximum value, that is 115. So this ensures that the section that we are having is basically what we can say as the compact section. So if our lambda s, the value of the slenderness limit that we are calculating, that is less than lambda sp for web is 115, lambda sp for flange is 16. So this ensures that our section is compact. So after that, the shear capacity that we shall be discussing very shortly, because shear itself is a very different concept, and that I shall explain you in detail. But before that, my intent was to explain you the how to calculate the bending moment capacity. So first of all, in here, if you're talking about the design for the what we can say bending moment. So effective section modulus clause 5.2.3. So ZE is nothing but one that we can refer from the code itself. Sorry, from the manual itself. So we can go to UB 610101. The grade is 300. And in here, what we can refer to is that. So this is approximately 2900, we can say, into 10 to the power 3 mm cube. So there is a little bit of difference, that I have taken as per the different, manuals. So overall, both of these values means the same thing. That is 2897. Instead of 2897, it is 2900 as per this particular manual. So you can ignore that and consider this 2897 mm cube. After that, nominal section moment capacity. Now nominal section moment capacity is different, and what we shall be doing is that we shall be calculating the reduced bending moment capacity also. But before that, we do need this particular value. So multiply this value 2897 with 3, the number comes out to be 869.1, multiplied with 0.9 again, this value is 0.9. So multiplying this with this particular value, we do get 782.2 kilonewton meter. So after that, if we are talking about the member capacity of the segments without full lateral restraint, so for that we do need to refer to section 5.6 of the code. So for that, what we need to do is that we do need to find out different kinds of bending moment, M2, M3 and M4. So this is basically center line moment, that is M3. M2 is basically first quarter point, and M4 is basically the third quarter point. So 0, 1 by 4, 1 by 2, 3 by 4, and in here we are having this as 1. So maximum, M2, M3 and M4, we got these values. So after that, we can calculate the moment modification factor. So this is the value that I had discussed with you a few minutes back under the, we can say, the written notes. So in here, we were talking about this particular value. We can say alpha M. So alpha M, we can calculate 1.7 times MM star. So MM star is basically the maximum moment in the segment. From this and this value, our maximum value is 273.6. So 1.7 into 273.6 divided by m2 square. M2 square is this particular value. M3 square, that is basically the square of this particular value, and M4 square, that is the square of this particular value. So whatever value that we are having here, or 2.5, whichever is the minimum value that we do need to take. So the alpha m value comes out to be 1.166. So this is basically the moment modification factor alpha m. So after that, the twist restraint factor KT, load height factor KL, lateral rotation restraint factor KR. So in majority of the cases, we can say that this particular value, that is load height factor, that is usually 1.4. But as of now, to simplify the calculation, I have taken all of these values as 1 only. That is considering the load at the shear center itself. So after that, effective length, that is basically 8 into KT, KL and KR. So it comes out to be again as 8000 mm. After that, if you're talking about the reference buckling moment, we can say M naught. So this is the equation that we had discussed theoretically here. That is this particular value. So we can calculate that is pi square into E is nothing 2 into 10 to the power 5. IY, that we can take it from what we can say this particular table itself, and divided with the help of what we can say as the IE. So that is basically the IY, and this is basically the LE. So pi square EIY divided by LE square. So that effective length LE that we have already calculated here as approximately 8 meters, and IY is a value that we can find out from the we can say property table itself. So what we can do is that this is basically the IY value, and this is 101. So this value is approximately, we can say, as 29.3 into 10 to the power 6 mm to the power 4. So that value that can be considered here, and that needs to be multiplied with G into J. Now G is basically the shear modulus, and J is basically the torsional constant. So G value is approximately what we can say as 80,000 MPa, and J is basically the torsional constant. That can again be calculated from this particular value, that is 719 to 10 to the power 3 m to the power 4. And in the second part in here, that is plus pi square E, we very well know, multiplied with IW and LE. LE we know that is 8 meters, that shall be squared, and IW is the one that can again be referred from this particular value. So in here, this is basically the warping constant IW, that is 2530 into 10 to the power 9 m to the power 6. So while putting all the values, you do need to ensure that all the units are same. So ultimately, the bending moment comes out to be, we can say, reference buckling moment comes out to be 357.2 kilonewton meter. But by calculating the reference buckling moment, till now the problem is we not completed yet. So slenderness reduction factor alpha S. So that also we had discussed when we were writing these notes here. So we have calculated reference buckling moment M naught. IY we had calculated from table. LE is the effective length. G and J. G we very well know, that is 80,000 MPa for structural steel. J is basically what we can say as the torsional constant that can be referred from the property table, and IW is the warping constant that also can be taken from the property table. We have calculated alpha m also, that is it is dependent on the bending moment diagram or the bending moment or the load application. After that, we do need to calculate the value of the alpha S. So considering alpha S basically 0.6, which needs to be multiplied with square root of ms divided by moa to the power 2 plus 3 minus the again same function, that is ms divided by moa. So MOA is this particular value, that is 357.2, and if we are talking about the MS value, so this is basically the MS value, that is 869.1, that is a nominal section moment capacity. So putting all of these values here, we do get alpha S value as 0.332. So as I said that alpha m and alpha s are interdependent on each other. So both of them needs to be multiplied and ensure that the value is less than 1. So alpha s is 0.332 and alpha m is 1.166. And when we multiply both of them, let us just calculate the alpha m into alpha s. So alpha s is 0.332 and alpha m is basically 1.166. So this number comes out to be 0.387, and that again needs to be multiplied with ms. So our ms value was approximately 869.1. So we multiply this value with 869.1. So the value comes out to be 336.6 kilonewton meter. That is the nominal member moment capacity, which again needs to be multiplied with 0.9 here to find out the design member moment capacity, that is 302.9. So this is the final value that we get to, or we can say, to calculate the final bending moment capacity for laterally unsupported beam. So that is like the basic calculation for this particular we can say moment capacity. Now interaction of shear and bending and the shear force itself, that we shall be discussing in the next lecture.